Okay, back again for the open response portion of the June 2016 exam, Common Core Regents. So what we're going to get into here, um, let's see, describe the sequence of transformations that will map one figure onto the other. So we have to start with this triangle ABC, and we have to move that. Make sure we do the correct order. Let's see, it looks like we're going to translate. Let's just make sure. What we have to do is make sure we get a sequence that takes angle A onto angle D, angle B onto angle E, and so forth. So looks to me like I'm going to translate to the right 6, and then probably, let's look at that. Yes. Perpendicular bisector, okay. So it looks like we're going to, initially it looks like we're going to translate right 6. And line reflect, or then line reflect. Now, what I've had in the past with students is sometimes that's all they'll say. And when we say describe the sequence of transformations, we've got to know that specifics are in order here. So rather than just say translate, line reflect, because we're not just looking for what transformations, we're describing the sequence. That means let's get some specifics here, okay, and let's show some work. What I would do first is you can write it out or use the notation, okay? We're going to be more specific. We're going to specifically say translate triangle ABC, right 6, and you don't have to say up or down because we're not going to get triangle A prime, B prime, C prime. Okay, so there's A prime, B prime, C prime. Hopefully you have a straight edge to do a little better job with it. Now we're going to show that we're going to reflect over the x-axis. And that is going to end up carrying A onto D, B onto E, and C onto F. Okay, so then we're going to line reflect triangle A prime, B prime, C prime over the x-axis to get triangle DEF. All right, and that's what's going to do it right there. A little more specifics, and if you're somebody that likes the symbols, okay, we could have done this. That'll do it too. Okay. All right. Let's see next. Okay, partition a segment question. Oh, it's off the graph, your typical graph. Now, I would take the scrap graph paper and test this out, but when they don't give a graph, it's kind of implied that you're going to be doing some algebra, probably, or some explaining. All right, I'm going to state the coordinates of P. So what I'm going to do is I'm going to give a quick sketch here. I'd much rather be on graph, but that's going to be off the graph. So I'm going to estimate 4.2 about there. And then way over here at 22.2 is where B is going to land. Okay. So what is this telling us? Okay, it's telling us that all the way from A to B is 18. And we got to find a way to make this 4 to 5. So P is going to be closer to A than B, but it's almost the center. So I'm going to estimate P right there. but we got to figure out exactly what that is. All right. So when you see a 4 to 5 ratio, yeah, you're going to need 4 parts here. You're going to need 5 parts there. What I like to say is that's a total of 9 equal parts, right? And since we have 18 units to get 9 equal parts, we're going to need 2 each. We're going to go 2 each to get to each congruent part. All right, so let's just estimate that here. That'll break it up into 4 parts. Let's try to make those about the same. That's 5 as well, right? Okay, so we're going to move from 4 to each. Okay, so we've got right there, that's where P is. It's looking like 12. One way to do this is to say 4 times 2 is 8, and 4 plus 8, because we're starting at 4, right? 4 plus that 8 is 12. So the point P is going to be 12, too. There's no movement in the y direction. It's all x. Okay. All right. For this one, okay, we don't know that AB is parallel to CD. One of the theorems we teach is the side splitter theorem. I don't know that that's actually something that is used statewide, so I'm not going to use that. It's just something we coin in our department. So I'm going to go with prove. It's a lot for 2 points, but I just don't want to leave any room for anybody to take points off here. So my goal is going to be to show that triangle AEB is similar to triangle sorry, get the order correct here, CED. So that's what my goal is going to be, to show that these 2 triangles are similar. That'll get us corresponding angles congruent, and of course that'll lead us to parallel lines. So that's the goal. All right, how do we get this? We're going to need the side angle side similarity postulate. And how that's going to work is we're going to add those together to get 8.75 and 10.5. Okay, kind of ignore these now for a minute. So we're going to start off with, all right, 3.75 to 8.75. Those are a pair of corresponding sides, right? So then that will equal, and I tested this already, so I know it does work, because the cross products are going to be the same, because their cross products are the same. And we'll show this. Okay, 3.75 times 10.5, and what were those? They were both 39.375. So that gets us basically the 2 pairs of corresponding sides proportional. Now what do we need? Well, we need this pair of angles. Angle E is congruent to itself by reflexive property. Let's see, now the triangles are similar. That's enough to get us a pair of corresponding angles congruent, so we can go ahead and say that. Triangle AEB is similar to triangle CED to D. Like that. By the angle-angle triangle similarity postulate. Okay, angle now EAB is congruent to angle C, because corresponding, let me get some more room here. Corresponding angles similar triangles are congruent. And because of that, AB is going to be parallel to CD, because when corresponding angles with two lines cut by a transversal are congruent, the lines must be parallel. Now that's way overboard for 2 points, but I don't know how else to do it without coming up a little bit shorter, leaving a hole in the explanation. So another thing we got to talk about here, explain kind of implies there's going to be words used. So make sure that you don't just leave it to the math. You have to explain the math a little bit. Not this much, but you have to explain it and do a thorough job. All right, let's see here. This next one's a nice problem. Usually we see it in a part 1, but again, we got to explain, so let's go for that. We teach our students this using probably kind of a pattern investigation type of thing. All right, we have them check out what sine of 50 close to 40. They notice it's the same. We develop this pattern, and then what they discover is that when angles are complementary, that means when we're in degree mode, measures add to 90 degrees. Okay, so when angles are complementary, their trig cofunction values will be equal. Okay, the reason, we show them the reason for this. So for this particular problem, if that's 73 degrees, okay, say this is 10 and this is 15. Better not do that, because I shouldn't just guess on that. Let's just call it A and B. Sine of 73 degrees is A over B, right? Opposite over hypotenuse. Well, if we do 90 minus 73, that's 17. The cosine of 17 is also A over B. So that is a little bit better proof right there that these are going to work out that way. So probably for my work, I'm going to say R plus 73 is 90. And, whoops. Let's try this again. A little too fast here. R is 17. So I've got R is 17. I've got a decent explanation there, right? So that's going to cover us. All right. Let's see. Oh boy. Radian measure. Okay, angles A and B just have to be congruent to have the same radian measure. Okay, just like degree measure, just a different format. It's radian measure basically is talking about how many radii it would take to cover this arc. So what we're going to do is, see if these arc angles are the same. and then we'll, if they are, then we have the same radian measure for the central angles. All right, so relative to their respective circles. So let's check this out. I am going to go with the circumference because arc length should go with circumference. This is how I do the problem. It's probably a better way. S equals theta r. If your teachers teach that, is way more efficient on this problem. But unfortunately, this is how I do this problem. I don't have them memorize a lot of formulas. S is for arc length, for those of you that didn't know. And the theta, that's going to be the angle measure in radians. So if you see this problem here, and r is, of course, the radius. If you see this problem here, it's way more efficient to use this formula. But I'm going to go with this just because that's what I use. Circumference is 2 pi r. So let's start with circle 1. Oops, not squared, just r. So that's 8 pi. All right. Circle 2. Circumference. Okay, so that's 13 pi. All right. Now, what I'm going to show here is relative to their circles, these arc angle measures are the same. So an arc length of pi for circle 1 to the circumference 8 pi, okay, is a 1 to 8 ratio. So this arc, okay, angle A, right, this arc, whatever it is, it's covering 1/8 of the circle. All right. Now, if we take a look at 13 pi and this arc length, so 13 pi over 8 to 13 pi, all right, if you reduce that, right, it's, again, it's 1/8. That's 45 degrees, or if you are in terms of pi, it's pi over 4 radians. Okay, so if you use this, you're probably going to get pi over 4 radians. All right, you know, the S equals theta r formula. So basically, if they're both covering 1/8 of the circle, okay, so if both arcs cover 1/8 of the circle, their corresponding central angle measures must be the same. Let's see. Okay, angles are congruent, so they must have the same angle. The same radian angle measure. Okay, so again, way easier if you learn this formula. Unfortunately, if you don't, then you've got to go through the circumference process. All right, so we have a ladder leaning against a building. All right, so this is your building. Make sure we identify that in the ground. Assume they're going to make a right angle. Okay, we can make that assumption, although that's not always the case. And the ladder is going to be leaning up against the wall. Okay, so from here to here is 10 feet. And it's 4 feet out, and they want to know this angle measure. All right, So now we're looking at trig probably. So this is the side that's opposite of this angle, this acute angle. This is the adjacent side. And of course, this is hypotenuse across from the right angle. All right, if we use our acronym, nothing involved with hypotenuse, so get rid of anything with h. It looks like tangent. So tangent of whatever theta is, it's going to be opposite over adjacent. So that's how our acronym works. Decide on the trig function, sine, cosine, or tangent. Then you have a side. Then the next letter is O for opposite and adjacent, and that's in that order. Opposite on top, adjacent on the bottom. Now this is tricky. I like to change this to a decimal. Not that it matters. It should still handle it the same way in the calculator. However, this is important. All of a sudden, when I teach students, it's strange how they get to the tan inverse of 2.5. Well, to make it simpler and more understandable is when we're trying to get rid of a function or like a multiply or divide, we want to perform the inverse operation. So we don't divide by tan because that's not the inverse of it. The inverse of tangent is arctan, or tangent to the negative first power. Okay. Now, when you do that, when you have functions that are inverses of each other, they knock each other out. Now, whatever we do to the left, we have to do to the right to keep that balance. And that's how we, all of a sudden this appears. Let's make sure we're showing that work properly. So tangent inverse, let me look at that. Gotta get to your calculator. I'm getting 68.1986. So it says nearest whole degree. Now we're looking at 68 degrees. Okay, let's try one or two more. Yeah, actually, I'll leave this for another video. All right, so that'll be the first few open response. I'll come back in a few to finish off the rest of this exam.